Thank you very much, and welcome on my part as well. It's nice to see you here in Estonia. My talk is going to be more about actual applications and ideas, less about maybe the principles which the previous presentation focused on. But I hope it's going to be useful and it's going to show you, create some ideas as well about where this thing is going, at least here in Estonia. Now the structure of the presentation is the following. I'm going to show you briefly, very briefly, where the data is coming from, and what type of data do we have, some sort of user patterns that we have seen there, because I'm from a research institution called the Center of ITP Impact Studies at the University of Tartu. So we are primarily researchers, but our mission is actually also to look at the data and think of new ways how to build services on top of that data, which are purely data-driven services. So I'm going to show you the usage patterns, then we're going to look at some actual applications that we did for the Estonian Tax and Customs Board using that data, and then a future outlook about a couple of projects that are currently in the pipeline, which are also purely data-driven predictive services using machine learning and AI methodologies. All right, now there is a lot of data available through the Estonian e-governance system. You probably, spending these 2 days here in Tallinn, have heard about it already, so I promise this will be, at least on my part, the first and last time you're going to see this slide about the X-road system, which you probably have heard of. This is the schematic picture of it. Simply to be on the same page, is simply a system where different registries exchange information over the internet, obviously securely in encrypted format. But this is basically I would say, called the Rosetta Stone of Estonian e-governance, because what's also in the system is a central log that has recorded all the transactions taking place on that system since 2002. And we as a research group actually have access to this central log. So we have been able to look at what kind of patterns do we see there. And let me show you very briefly some of these patterns, and then we're actually going to go and look at specific applications or prototypes of applications. All right, this is just as an information, this is the development of the number of e-services that then run on X-road. This is the blue line, which you see there. Currently, it fluctuates a bit, as you see. The number of e-services hovers around 1,500, 1,700 services in the latest year. And as I said, the system basically exchanges information between different databases, different data sources, different registries. The number of registries and then data sources on that system currently hovers around 250 sources. So actually, in terms of like global scale, probably might sort of strike you as nothing, but actually it's a very big system in Estonia, given the smallness of the country. And what does this system produce? Then basically people go about their daily lives, obviously consume these e-services, and we simply see the log traces of it. This is the aggregate picture of the total number of queries being produced by the users of these e-services. The latest, as you see, it grows exponentially, still is growing currently as well, and has hit around 500 million queries a year. Again, might seem like a small number, but we do not know precisely, but we estimate that around 1/3 of these actually involve a human, meaning some sort of human interaction is involved. So it's actually a very big number given the smallness of the population. We only have talking about 1.3 million people using these services. So the usage is quite intensive. And when you start to look at the actual log traces of these specific people, the actual individuals, then we see that again, all basic graphs that you're going to see on my part today always grow over time. The upper line, the red line, shows the number of unique individuals on that system on any given day over time, over the years. And currently we see that around 2% of the population on any given day uses at least one e-service, and it's obviously still ongoing. And these are only services running on X-road, so obviously there are others of the system as well which are being used. So actually it has spread a lot. And the penultimate slide on the usage, this shows the diffusion rate, meaning that we have looked at what share of people are using these services over time according to age, for example, here. And you see that actually, again, it grows, meaning if you, let's say, if you take the last graph from 2015, because we have the logs from 2005 to 2015, the latest ones are still coming in, you see that the usage rate is around 80% for the age group between 20 to around 50 years. So 80% of people are using at least one e-service, and the oldest user groups actually are coming as well. Slowly, but coming. Obviously not the youngest ones. Kids don't really use e-services, or if they appear in the logs, then because their parents are consuming certain types of services where the kid is actually attached with the ID as well. But diffusion clearly has been there. And finally, the final sort of sociological slide before we go to actual applications is this is the number of services on how many days they are being used. Let me just walk you through the slide, through the graph briefly. On the x-axis is the number of services. So what you see over time is slowly the density of the points expanding around the x-axis, meaning more and more people are using more and more services over time. And on the y-axis is on how many days in a year have they been using these services. And you see an expansion there as well. And what you also might notice is actually seem to have two types of sort of user groups. The most intense region is actually always sort of from your point of view, the bottom left corner, meaning people use a couple of services on a couple of days. Because when you think about it, these are government provided services. How many times do you actually need to interact with the government? Actually not very often, or at least you wouldn't like to interact very often, because if you would have to, then probably would indicate that there's a problem somewhere. So we have people at the lower left corner, a lot of them, and actually there's another user group who uses a lot of services on basically on almost every working day, and these, the log traces show, tend to be from a specific social demographic group, meaning mostly actually people employed in the public sector from the specific age group. So they are using these services because of what they do actually for a living. Now, we have a lot of this data over time, logged, archived. So the question arises is what to do with this data, obviously on top of simply providing services on a day-to-day basis. Maybe we can actually add value, more value to that data, because this is very useful data, because it's basically a snapshot of the whole society functioning on any given day. And one idea or one project that we recently finished together with the Estonian Tax and Customs Board actually takes this data and builds applications on top of that use different machine learning solutions in order to actually make smarter, faster decisions. So let me walk you through some of these applications, but before I do that, I'm going to show you where the actual data for these specific applications then comes from. Now this is tax revenue in Estonia. And again, this was a piloting project, so we were given access to tax declaration data up until 2016. And if you look at this, what sort of should strike you out, obviously the smallness as well. Again, I mean 6 billion euros in 2016, it's a small country. But if you look at the percentages, then over the years, it depends slightly, the slight fluctuations, but with around 98% of this tax declaration data is handed in voluntarily. And only around 2% actually comes in through the intervention of the taxman. So obviously tax compliance is, well, close to perfect. But what also is close to perfect when you think about it is actually because the companies, which this shows the company tax declarations, hand in these declarations on a monthly basis. So they're not only paying very well taxes on a monthly basis, but they're actually handling over huge amounts of information on a monthly basis as well. So maybe on top of the taxes, we could actually do something in addition with this data. There are around 166,000 companies and institutions that are subject to these taxes. Again, last time I'm going to say it, small country, which is basically the whole population of these institutions in Estonia. And the Tax and Customs Board has very good comparable data going back almost 16 years on all these institutions and companies. So we have in terms of big data, actually it maybe isn't so big, but if you think of the units of the companies, this actually is already quite a lot. We're talking about the billions of observations on actual economic activity of specific companies. And the idea behind this project, the applications that were built, was to monitor it in real time, meaning that we would not like to wait until the official statistics come in, because official statistics tends to come in with a significant lag. But you need to make decisions today about, let's say, specific economic policies, specific tax exemptions, etc., etc., etc. So we would like to have a picture in real time as fast as possible, but the declarations are handled basically in real time in terms of economic activity on a monthly basis, so the data is there. Maybe we could use it to monitor that the economy in real time as well, so monitoring. Obviously, also providing input for probability-based decisions, meaning that, let's say, when you are an institution that handles out export subsidies, companies apply for these with specific projects. Maybe we can actually look at the data and see who has a higher probability of exporting, given the data that we have, and have not like a machine making a decision, but actually having the probability-based input for the civil servant to say that this company applied for this subsidy and also has a very high probability that they will start to export, even though they haven't done it so in the past. Meaning we mine the data, and maybe we can actually target these subsidies more efficiently, actually. They would bring more benefit to the society and the economy as such as well. And also forecasts for planning. So let's look at one specific forecasting application. Now it uses this value-added tax declaration. It also uses declaration data on all these companies. Also something that is referred to as a value-added tax information declaration, which is again quite unique. All Estonian companies who engage in transactions with each other in excess of 1,000 euros need to declare these transactions. So we not only know what the company, basically what the economic activity of the company has been, but we can actually connect companies. So we have a picture of the network, the complete network of the economy. So this data is also being used. Social and labor tax declaration, business registry, VAT subject registry, and some outside data as well, like demand data from Eurostat and from an Estonian economic research institution as well. And this is what the sort of the structure of the projects look like. The data comes in anyway for tax purposes, so we do not need to do anything with that. What we simply do, and what we have done, we have built two analytical layers on that. One is the sort of preparation code, if you want to put it that way. It's basically, this is a piece of code that takes the raw declaration data, reformats it slightly, recodes it, and feeds it into a machine that then does the modeling and visualization. And we built a set of apps that basically look like this, sit on top of the declaration data. Without any intervention, actually, how the data is being gathered, meaning it should be as non-intrusive as possible. No one would have to start to submit declarations in a different way. No one would have to start to demand specific types of data from companies in order to do this forecast. Let's simply use what is coming in anyway. It's always up to date. Given that the data is updated, it's simply a matter of refreshing these forecasts. And it's also very easy to develop new applications, because if, let's say, a specific institution is interested in some part of the data which they need for their own business process, then we can very fast build an app that goes to the declaration data and then fetches that data, reformats it, and visualizes in a way, or produces some sort of output that they can then use. So the forecast application, which is a screen capture video of it, looks really simple. What the user can do, it can select the classification of the economy. You have different aggregation levels, so you simply select the aggregation. After that, you select the actual sector. So obviously we're going to select ICT, given the conference that we are in. So you use the sector, then you choose what do you want to be forecasted. So let's take the total economic output of the ICT sector. You can select the range of the forecast from 1 month to 12 months into the future, so in 1 year's time. You can select the training period, and you simply click on Run. And what you see now, there's a progress bar running on the bottom right corner. This is actually, it's not working on that computer because of the sensitivity of the data, but it's actually in real time. That's how fast it works. So what the application does now at the moment, I'm going to tell you about the model behind it as long as it runs, and then you're going to see the results. It starts to fit different models on these declaration data, ICT companies, and then the outcome is total turnover. And the idea behind it is very simple. If I would ask you here in the crowd, what is going to be, let's say, the economic growth of Estonia next year, and each and every one of you would give me an estimation, your best guess, and we would come back next year to the same conference here in Tallinn. I hope you're going to do that, and we'll see who was right. Then each individual one of you would be wrong, slightly. But if I would take the average, I'm pretty certain that you would be spot on. And the model actually does the same thing here. It fits different statistical models because the economy actually tends to, depending on the sector, behave quite differently over time as well. So it fits different models and learns at the moment weights for these different models in order to combine them into one single prediction that is the most accurate one. So that is what is being done at the moment, basically an optimization of the weights. And in a second, the progress bar is almost finished. You're going to see the actual results. There's going to be a black line, which is going to show you the actual turnover of the ICT sector in Estonia. And in a couple of seconds, I was should have tied my talk a bit better, but the upper coral line now, which you see overlapping actually with the black line, is the forecast that was now issued 1 year before the data actually came into being. And you see, it is very precise, actually. These machine learning solution manages to get it spot on. These are the forecast of these specific different models, which I gave an example with you. So you can see that at different time points, they indeed, some work better, some work worse. So the combination comes from these weights, and you see the red line area here, which is a model that was weighed up, and other models which were weighed down as well. You can look at the diagnostics, how well do specific models work. You can look at decomposed effects, what are the seasonality cycles, etc. in the economy, and you can look at the actual forecast of each and individual model as well. And if you want to, you can run your own models as well. But the idea behind it is to scale modeling, scale machine learning, and make it available for the interested parties who actually need that input, but cannot run the models themselves because they simply do not know to. What has been happening previously or in the past is that these models were run by obviously statisticians and specialists from different ministries, different institutions that fitted these models themselves. But as you understand, people do not scale very well. So if you tell an economist that, sorry, in order to plan the budget, I would now need you to forecast 100 sectors. It's going to take a lot of time. What this solution does is simply a couple of mouse clicks away because it fits the same models, very similar models that a trained economist actually would do. But it would take them in excess of many months to do that. Now it happens within a couple of minutes. And it's very precise, surprisingly precise, obviously depending slightly on the sector as well. I'm going to show you now another short video of another application because if you remember back, I said that there's actually a picture of the complete network of the economy available as well in Estonia. And the need of the public sector was to basically to run risk scenarios on actual data in order to see what happens when some large companies suddenly fold or cease production, which obviously you can see the headlines coming quite fast, so you know how many people will be laid off in that specific company if they, let's say, close a specific factory because of world market prices for their goods. Sometimes it might happen. but you do not actually know what are the implications for the larger economy, given that these companies might actually be really, let's say, the #1 buyers of a product from a company from a completely different side of Estonia or country, where this other company actually happens to sell 100% of the products to this specific large company that now folds suddenly. So you have these unexpected events occurring all across the country, which you do not know because you do not actually know, you do not see the network because you haven't visualized it, you haven't modeled it. So what the application does, it takes this network data of the complete economy and shows what you see here is the ego network of one specific company. Company is in the center and all the dots around it are companies that are either selling to this company or buying from this company. And what the application simply does, in the table you see also a list of transactions, all of these transactions in that specific network. You can see the user can simply delete the company and all the transactions are recalculated and the effect on all these business partners are shown, meaning you can start to see how much or whether certain partners would have to lay off people given that the transactions with this specific company that now suddenly disappeared makes up, let's say, 90% of the total monthly turnover. So you would have to notify that company or notify that region where the company is sitting that actually there's a catastrophe coming or social sort of a catastrophe coming because you are so central to the specific region. This is sensitive, meaning that, I mean, you can take pictures if you want to. The ideas are obviously artificial. This type of information includes obviously business secrets, so that solution cannot be made public, whereas the forecasting one can be. So this will sit or is working at the tax and customs board at the moment. But when you think about it, we have these ego networks for all these economically active companies. And we can also connect these ego networks with each other if these two companies, for example, have done some transactions with each other, thanks to this declaration data. We can connect these companies or these companies. So we actually have the whole network structure, and we have all the pictures or all sorts of pretty good understanding of what is actually going on within this company as well. So if you are, let's say, I don't know, I presume there are some people with a background in economics as well. There are methods available, traditional ones already, where you can model specific outcomes, time series from other time series. I mean, I'm not getting too technical here, but when we think about what the data actually is comprised of, then you could technically start to model the complete economy on the individual company level in Estonia. Technically, it would be possible because the data is now there. Since 2015 when this rule was introduced, mainly for tax compliance reasons, but actually in terms of data usage it's actually something of a coal mine as well, which we are still sort of learning to get into because the data volumes are actually huge, so the methods, the traditional methods do not work very well, do not scale very well on that data. But I would say that we are fast moving into that direction, meaning we would see that all companies obviously are separated, let's say, I don't know, by 6 degrees of separation. So we see what happens in this specific company and we can see and model what is going to happen once this company does something, if we add a subsidy to this company in order for them to expand production. Where is the benefit actually going to come from? Not only from directly this company, but how it spreads. And based on that, actually make decisions, meaning that target all these schemes into companies or clusters of companies where we can see already based on the historical data that that's where the maximum impact could come from. All right. So much on this real-time economy, because I'm not going to show you the other applications. We build a set of them which sit in the tax and customs board, but these are all standalone simple applications in a sense. Or simple, I would say, maybe is not the right word for it. Computationally, they are quite intensive and quite sophisticated, but they are all point-and-click applications, even though there's some machine learning solutions underneath it. And let me also very briefly talk about a couple of ideas in the pipeline which also used and this data that is being produced anyway. Again, in a similar format, we simply build a data analytical layer on top of this data. which then use machine learning and are predictive in nature. For example, I mean, there's a sunny day out today, but I don't know if you had the not so good fortune of being here in Estonia, maybe in the winter. It's not so nice. The weather is pretty bad. But what we have, this picture of the map of the country, and these dots which you see here are road weather stations. Road weather stations run by the National Road Administration, which log a lot of data on the road condition in real time. In real time, I mean, most of them actually log it after every 15 minutes, and they log actually surprisingly lot. They probably cannot see it from the resolution. Let me simply show you. One of the weather station is clicked open. Here it shows you the road status, whether it's dry or not. It shows you moisture, air temperature, road temperature, wind speed, and visibility in meters. Some other stations also log the average speed of the cars passing through this specific road section, the share of heavy transport as a percentage, dew point, you name it. I mean, a lot of information actually. And this sits freely on the web. And on the other side, you have accidents happening, which are logged by the Estonian Rescue Board. And I've seen the data again. This is sort of quite sensitive, but they actually log very precise information on all kinds of accidents. And this January was particularly deadly in Estonia, and only in January we had 10 traffic fatalities. Again, okay, I promised not to say it anymore, but really the last time I'm going to say it. It's a small country, so 10 people. Actually, that's quite a lot, because in 2017 we only had, if I remember correctly, a bit below 50 fatalities in traffic accidents. So this year, only in January, already 10, so it's a lot. And when this deadly month of January happened, and there was a lot of discussion what to do about it in order to prevent these deaths. Many ideas were forwarded. One was that actually we would need to improve the road conditions faster. As snow comes, we need to clear the roads faster. And there were calculations made which said that it would cost around 60 million euros a year to have the readiness, let's say, within half an hour to clean all the roads. We would need an access, in addition, 2,000 basically road clearing vehicles, and we would need around 3,000 drivers for these vehicles. So 60 million euro price tag. Now, when you think about it, what the idea is, basically the project has been already basically kickstarted, is to take these two data sets, which one is the set on the traffic conditions, the road conditions, and the other one is simply again a table of accidents. So two data tables. Let's say you can think of it as two Excel tables. And match these two and see whether the road conditions actually predict or give us a very sort of a rough estimation of the probability of an accident happen within on that road condition, on that road section, given these conditions. And maybe instead of 60 million euros, you actually develop an app for 2 million euros and show the driver, which is the number one cause behind accidents, is not bad road conditions, but a driver plus bad road conditions. So if you could influence the driver, the behavior somehow, that would make a difference. So you can make the roads better for 60 million euros and hope people will drive more carefully, or you can try to affect the individual between the wheel and the seat, which makes the decision. So if you run a model that actually learns in real time what is going to happen in these sections given these road conditions, using these two databases, and display that information back to the driver. As the driver enters this road section, simply in Waze or Google Maps, there's a warning says that, watch out, you have entered the road section that has now this and this probability of an accident occurring, which should actually maybe make you slow down. So you can influence the individual driver, but also you can send that information back to the National Rescue Board, who said that we have now within this road section at these conditions a critical situation, send a police patrol to calm the traffic there in order to avoid actually this accident going to happen anyway. And the final idea before I wrap it up, and there's time for questions as well. This is another project in the pipeline with the National basically Rescue Service. They would like to see whether we could predict, using the available data, the probability of different fires occurring, house fires mainly, of objects, meaning that buildings then, where people live in, not industrial buildings, but people where people actually reside in. We know the building registry. There's a lot of information what the technical, basically how the building actually looks like, what materials are being used, how old is it, what is the heating system, what is the electricity system, all that information sits in that registry. We also know the rescue data, where the actual calls were made, where the actual accidents happened. They do a lot of home visits. They do around 20,000 home visits a year, so we actually know also what are basically the socio-demographic sectors where these dangers are the largest ones. And we also have additional data like the weather, local weather, which makes people use different types of heating systems, which actually increase the fire hazard. So if you put all that data together, and again, in real time, predict then what we might actually see, because all these Estonian let's say, fire stations, they actually have a specific area where they are obviously responsible for, and they know quite precisely, depending on the road conditions, how fast would they get to that point. Meaning that is the area of readiness. And when we now would actually also issue these fire hazard scores for all the objects within that area, then we would start to see that actually, whereas the readiness of the fire, let's say, trucks is constant, the actual danger area moves in and out of the readiness area, given time of day, because when people drive home, then actually this start to cook, for example, then we know that the fire hazard increases. Given the week, it's higher in certain areas in weekends, lower in certain areas in weekdays. Given the season, definitely obviously higher in winter than in summer, again, depending on the type of building, type of people who live there, etc. So we actually start to see how the hazard is very mobile, whereas the fire station is stationary. So maybe through these applications, actually, we can build better readiness, meaning there's this short-term readiness of the firefighting crews. Basically, they know that the specific types of areas will now light up, and they need to do something about it. And long-term planning as well, meaning that they might actually see that certain areas with very high fire hazard are actually out of their basically effective reaction time, and we would need to move the company or do something in addition in order to mitigate these risks. But I would call it there, and there's still time for questions. Thanks. Yep, please.
Jeremy Millar from Denmark. I missed the beginning, so I apologize. But I know in the US, for example, in some European countries, they have a system where they have 311 data, which means that this is really where people call in with complaints and questions, and that's a huge data resource. I know we do in New York and other places, Philadelphia, and this can be combined with other databases to make predictions about what they think is going to happen in terms of crime, in terms of accidents, in terms of all sorts of issues, right? And they can then make sure that using predictive modeling and in the way you described, that the police are ready and they know that they're going to have highest peaks in this time of day or this month of the year and other, so they can really plan their resources and their responses in a much better way and save millions of dollars, right? In that sense, I guess you're talking about something similar. Do you have anything like the 311 system in where that big database could be matched with other ones?
Yes, technically it sits within the National Rescue Board who takes all these calls. So I mean, whether it's people need an ambulance, police, or the fire department, they call one number and it's all being logged. Now I don't know how much this unstructured information is there, but a lot of this information obviously is structured as well, meaning that it's already numeric, it's being recoded or entered once the call is being taken, and it would clearly help with, let's say, this is, I mean, like fire hazard scoring. What you are referring to is basically predictive policing. Yes, it could be there, used to be there as well. It's not currently being used, actually. The Estonian police has made the actual crime statistics, what you are referring to, are basically something that, well, not really like happens before, but it's not like the actual recorded crime, but how would I put it? I mean, it's something else. Let's say the recorded crime is within that as well, but it's everything in addition to that as well. The Estonian police has made that data, obviously in an aggregated format, available as open data. So you can go and visualize where the actual crimes happen. And multiple visualizations already out there as well. The next step would be to actually not take the aggregated data, which in terms of modeling usually isn't very useful unless you want to simply issue some aggregate crime statistics, which is not what you want to do. You want to prevent actively these things from happening, is to go to the raw data and actually try to see whether these algorithms might indeed predict that, because in terms of data science, from a point of view of data science, it's simply yet another output, nothing else. I mean, it's a 1 or 0, whatever you want to call it, a classification problem, empirical question whether the model works or not. Is it a fire hazard? Is it a burglary? Is it a speeding offense? Whatever. The information technically actually is already there everywhere. Okay.
Abandoned cars in the street. So it's another huge database which can really be used not just by the police or the emergency services, but also by the other municipal workers who have to deal with these things anyway. Right? So, as I say, it saves billions of dollars, I think.
Basically, yeah. I mean, it would be like a database on the demand of the citizen for specific services or lack of specific services. Yeah, it's good in a sense because I mean, it's always very expensive to gather specific data for specific purposes. You need to design the data gathering process, etc. It's simply expensive. So if you have data that is being, for whatever reason, recorded anyway, it might not be the perfect proxy, a perfect measure for it, but it's a proxy. So why not use it? I mean, it's a very, let's say, cost-efficient way how to build things, because especially these initial stages of any data science projects do not really need to invest a lot. You simply need to get the data and put a team of data scientists on it and see, I mean, what comes out, what not. And once they, let's say, prototype it and see that these models seem to work, then obviously you need to put some development money into it to build an action application that does that. But yeah, I mean, would be perfect. I mean, some sort of measure of the whole society, the demand of what is going on, or the lack of specific services. Yes, there's a question.
Hello, I'm Segru, actually from Georgia. I'm interested, did you process information from health sector, and if yes, what are the results?
I've showed you in the beginning these extra logs. The actual health records are not recorded there, but for example, what is recorded there is digital prescription. And we have in Estonia this digital prescription basically means paper-free. You go to the doctor and it's recorded in a database. You go to the pharmacy, simply identify yourself, you get the medicine. In that sense, a very simple e-service, simply takes the paper away. But you can build new services on top of that actually still, because then you start to see what came out, for example, what wasn't known before that system was put in place, how many prescriptions actually go to waste. We know that there are around thanks to this data, we know that there are around 11 million prescriptions issued a year, prescription medicines in Estonia, for a population of 1.3 million. What came out, because previously the databases weren't connected, what came out is that actually only around 9 million end up being bought in the pharmacies. So there's a discrepancy of 2 million prescriptions being issued by the doctor, which are not being used. And if you think about it, issuing a prescription for the doctor, basically, I mean, we actually have quite precise data. It doesn't take long, it takes less than a minute. But this is not simply 2 million times a minute time that is being wasted, but this is actually a doctor's visit that was now wasted. And if you think about it, that, I mean, a doctor's visit usually mostly, it probably doesn't take less than half an hour. So if you multiply 2 million with half an hour, that's already a lot of time that is being wasted. So maybe with this data that we see in the logs, we can identify who are these people and what are the possible reasons why these prescriptions are going to waste. Meaning that maybe we can actually design the prescription issuing process in a way that we would reduce that waste.
Are you going to collect more information in this part? For example, diagnosis-related information, what are the main diagnoses for which people go to hospitals and so on?
Technically, the information is all there in the National Health and Health Insurance Fund actually records basically everything. We have e-health record. So we would not like to record anything in addition, simply use the information that is available. If it's in different databases, then combine it, and I would say the possibilities are, I mean, it's a platitude, but I would say limitless clearly, because this data can show us a lot of inefficiencies, and it's a very huge sector of the health. I mean, it's one of the largest items on any budget. So the data, even increase in efficiency of 2%, we are talking about hundreds of millions already. So it's a huge impact.
Thank you.
But I think, unfortunately, we're out of time. So I'm happy to talk to any of you later on or after the break. Right? Thank you.